When security requirements are written well and analyzed carefully, they still have one more hurdle before they become real. They must be translated into something engineers can build without guessing. That translation happens through functional analysis and allocation, which sounds formal, but the core idea is simple and practical. Functional analysis is the process of breaking down what the system must do into clear functions and subfunctions, so you can see exactly where security-relevant actions occur. Allocation is the process of assigning those functions, along with the security requirements tied to them, to specific parts of the system, such as components, services, interfaces, or operational procedures. This matters because security fails most often in the space between intention and implementation, where everyone assumes someone else will handle a requirement. By learning how functional analysis and allocation work together, you learn how to move from security as a document to security as a built-in behavior that can be tested, monitored, and maintained. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A strong way to think about functional analysis is to treat it as the bridge between mission statements and actual system behavior. At the top, a system exists to do a few big things, like store records, process transactions, or deliver information to users. Under those big things are the specific capabilities that make the mission possible, such as creating accounts, validating input, retrieving records, updating records, generating reports, and managing administrative settings. Functional analysis makes those capabilities explicit and organized, so you can reason about which actions are routine and which are high impact. For security, the high-impact actions are the ones that, if misused, would cause major harm, like granting privileges, changing access rules, exporting large datasets, or disabling monitoring. Beginners often focus on the visible user features, but functional analysis forces you to also capture supporting functions that matter just as much, like identity verification, session management, audit logging, and recovery workflows. When these functions are clear, security requirements can attach to real behaviors rather than floating as abstract statements that nobody knows where to implement. Once you have functions identified, you can start to understand what it means for security to be implementable. A requirement like enforce least privilege is valuable, but it becomes implementable only when you can point to specific functions and say who should be able to do them, under what conditions, and what data they touch. Similarly, a requirement like log access becomes implementable when you can define which functions constitute access events, what details must be recorded, and where the logging happens so it is reliable. Implementable security is not a new kind of security. It is security that has been connected to actual system activity. This connection prevents a common failure pattern where the system has strong protections around login, but weak protections around what happens after login, because the team treated authentication as the whole security story. Functional analysis makes it obvious that authentication is only one function in a larger chain. When you see the chain, you can protect the chain. Functional analysis also helps you detect hidden complexity, which is important because complexity is where security gaps like to hide. A system may appear to have one feature, like allowing users to view their data, but under that feature are multiple functions: searching for records, filtering, caching, formatting, and possibly calling other systems to enrich the display. Each subfunction can introduce data movement, new trust boundaries, and new opportunities for mistakes. If you treat the feature as one big black box, you may apply a requirement only at the outermost layer and miss that internal subfunctions handle sensitive data differently. By breaking the feature into subfunctions, you can decide where validation must occur, where authorization must be enforced, and where sensitive data must be minimized. This is especially important when systems are built from multiple components, because each component may only see its own part of the work and assume other components handle security. Functional analysis makes the end-to-end behavior visible, reducing those dangerous assumptions. Visibility is the first step toward consistent protection. Now consider allocation, which answers the question of where security happens. Once you know the functions, you allocate them to parts of the system, meaning you decide which component performs which function and which component enforces which security requirement. Allocation is not only a technical activity, because some functions are operational, like reviewing logs, approving access changes, or restoring from backups. If you allocate everything to software and ignore operations, you end up with gaps where nobody owns essential tasks. If you allocate everything to people and ignore technical enforcement, you end up with security that relies on perfect human behavior, which is not realistic under stress. Good allocation creates a balanced model where software enforces what it can enforce reliably, and people handle what requires judgment, with processes designed to reduce error. Allocation also helps manage accountability because it makes ownership explicit, which is critical when something goes wrong. When ownership is explicit, improvements are easier because you know where to adjust design or process rather than blaming the entire system vaguely. A key reason allocation makes security implementable is that it turns broad requirements into specific responsibilities for specific system elements. If the requirement is to protect data confidentiality, allocation clarifies which components may access the data, which components may transform it, and which components may export it. If the requirement is to preserve integrity, allocation clarifies where validation happens and where integrity checks are enforced. If the requirement is to ensure availability, allocation clarifies which components must be resilient, which dependencies must have fallbacks, and which recovery actions are required operationally. Without allocation, requirements can be interpreted as general intentions that do not map cleanly to build tasks, and then they get implemented inconsistently or not at all. Allocation also supports testing because testers can verify that a component performs its allocated security responsibilities, and they can detect when a requirement was allocated nowhere. That is a powerful concept for beginners. You can find security gaps simply by asking, who owns enforcement of this requirement, and where in the system does it happen? It is also important to understand that allocation often reveals design decisions that must be made to support security. For example, if you allocate authorization enforcement to a specific service, you may need to design a clear interface so other components cannot bypass that service and access data directly. If you allocate auditing to a central mechanism, you may need to ensure that mechanism is protected from tampering and is available even when other parts of the system are degraded. If you allocate credential management to a secure subsystem, you must ensure other components do not store secrets in unsafe places or reuse credentials in ways that defeat separation. In this way, allocation is not only a mapping exercise, it is a driver of architecture. It forces you to build boundaries that make your allocations meaningful, because allocations are only as strong as the separation and control points that support them. A well-allocated security design makes the secure behavior the natural behavior, rather than an optional behavior that can be skipped under pressure. Functional analysis and allocation also reduce misunderstandings that happen when different teams build different parts of a system. One team may build a user interface and assume the data service will enforce access rules, while the data service team assumes the user interface will filter requests correctly. If both teams assume the other is enforcing authorization, the result is a gap where nobody enforces it consistently. Allocation prevents this by explicitly stating that authorization is enforced in a particular layer, and other layers must treat that enforcement as non-negotiable rather than optional. Similarly, a logging requirement can be lost if everyone logs partially and nobody logs completely, producing scattered evidence that cannot be trusted. Allocation clarifies which component is responsible for producing authoritative logs and which components must provide supporting context. This reduces duplicated work and improves consistency because each component knows its job. For beginners, this shows why security is an engineering coordination problem as much as it is a technical control problem. Another subtle benefit is that functional analysis helps you identify where security requirements should be refined or split. Sometimes a single requirement covers multiple different behaviors that do not belong together. For example, a requirement to control access may need to be split into separate requirements for authentication, authorization, and privileged action approval, because each maps to different functions and may be allocated to different components. A requirement to protect data may need to distinguish between protecting stored data, protecting data in transit, and protecting derived outputs, because each has different enforcement points. Functional analysis provides the clarity to make these distinctions without turning requirements into a confusing mess. The goal is not to create more text. The goal is to create requirements that match how the system behaves. When requirements match behavior, allocation becomes straightforward and validation becomes realistic. When requirements are lumped together, allocation becomes guesswork, and guesswork is where security drift begins. As you allocate security responsibilities, you also need to consider trust boundaries, because boundaries determine where controls must be enforced to be reliable. A trust boundary is where data or commands cross from a less trusted area to a more trusted area, such as from a user device into a server, or from one service into another service that performs sensitive actions. Allocation should place the strongest checks at trust boundaries, because that is where untrusted inputs become system behavior. If you allocate critical checks too far away from the boundary, you risk having bypass paths where requests sneak around the checks. For example, if validation is only done in a user interface, an attacker might bypass the interface and send requests directly to a backend. If authorization is only done in a downstream component without clear enforcement, an upstream component might accidentally expose unauthorized data through a shortcut path. By allocating checks at the correct boundary, you make them harder to bypass and easier to reason about. This boundary-aware thinking keeps security consistent as the system grows. Allocation also has a time dimension, because security must hold not only during normal operation but also during maintenance, upgrades, and incident response. If you allocate security controls without considering how changes happen, you can create a system that is secure on paper but fragile in practice. For example, if a recovery process requires bypassing normal access controls to restore data quickly, you must allocate accountability and safeguards for that bypass, or it becomes a permanent backdoor. If updates require privileged access, you must allocate controls around who can deploy changes and how changes are reviewed, or an attacker who compromises one account can push malicious updates. Functional analysis helps by identifying maintenance functions as real functions, not as afterthoughts. Allocation helps by assigning those functions to controlled roles and processes with logging and oversight. This is how you prevent operational shortcuts from becoming structural weaknesses over time. Beginners sometimes assume that allocation is a one-time decision, but in living systems it is revisited as the system changes. New functions appear, old functions are modified, and components are replaced, which means allocations must be reviewed to ensure requirements are still enforced. This is not a sign that the original allocation was wrong. It is a sign that security engineering is tied to change management. A well-designed allocation model actually makes change safer because when a component changes, you know which security responsibilities must move with it. If a data service is replaced, you can ensure that authorization enforcement and audit logging responsibilities are preserved. If a new integration is added, you can ensure that trust boundary checks are allocated to the right point. Without allocation, changes tend to be risky because security responsibilities are implicit and can be lost accidentally. Allocation is therefore a tool for stability, giving teams a way to evolve systems without losing their security posture. Another valuable way to judge whether functional analysis and allocation are making security implementable is to ask whether engineers can validate their work without debate. If a requirement is allocated to a component, the team should be able to define what evidence shows the requirement is met, such as behavior observed during controlled tests, records produced by audit logging, or monitoring signals that confirm enforcement. This evidence-based mindset discourages vague allocations like everyone is responsible for security, which usually means no one is responsible for specific enforcement. It also discourages allocations that are impossible to validate, such as relying on user behavior as the primary control. Implementable security leads to measurable security, and measurable security leads to maintainable security, because you can detect drift and correct it. For beginners, this is a major insight. The purpose of all this structure is not bureaucracy, but the ability to build and prove trustworthy behavior repeatedly. As we close, the main thread is that functional analysis and allocation turn a security requirements baseline into a buildable plan that can survive real-world complexity. Functional analysis clarifies what the system actually does, including the supporting and high-impact functions that attackers and failures will target. Allocation assigns those functions and the relevant security requirements to specific components, interfaces, and operational roles so that nothing important is left ownerless. When done well, this approach reduces conflicts and ambiguity, strengthens separation and least privilege, and makes validation practical rather than theoretical. It also supports change over time by preserving security responsibilities even as the system evolves. For a beginner, the habit to cultivate is to stop treating security requirements as floating statements and instead ask, which function does this requirement affect? Where is that function implemented? And who is responsible for enforcing and proving it? When you can answer those questions clearly, security becomes implementable, and implementable security is the kind that holds up.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.